In this lecture, we're going to talk about the most widely used learning algorithm called artificial neural net, which essentially mimics human brain in terms of structure and learning process. It's been a very powerful learning algorithm for over 2 decades now, and now it is experiencing a big resurgence by advancing it into the recently popular deep learning model. So we're going to start by a motivation for the need of artificial neural net model for learning as we encounter problems of overfitting for the logistic regression model, which we had back in lecture 7. We'll then begin with the simplest artificial neural net structure called perceptron, which is by and large the logistic regression model with having a single layer on nonlinear mapping. And then we'll build the model into multi-layered artificial neural net structure by adding more nonlinear mapping layers. The power of learning process in artificial neural net has been made possible by the backpropagation algorithm, which essentially tries to map how the error values in the back propagates back into the front end, which is accomplished by gradient descent iterative process. So this is something that we're going to address and describe the procedure in detail here in this lecture. We can appreciate the power of artificial neural net by recognizing the limitations of the logistic regression model in a simple classification task. For example, here in this mapping between the negative samples to that of the positive samples in this two-dimensional space, x1 and x2, what we did back in lecture 7 was using this nonlinear hypothesis, which is essentially a sigmoidal function for performing classification. That is to be able to obtain this decision boundary by mapping, as you know, the linearly related parameter in terms of its dot product with that of the feature in this form, and then we mapped it with, once again, this sigmoidal function. Now, inside of this bracket, as you can see, is a linear relationship between the parameters and its corresponding feature. Now, here for the two-dimensional space, x1 and x2, what we did was that we had these polynomial terms, for example, the quadratic terms of x1 squared and x2 and so forth, or x1 squared times x2 squared, and all these polynomial functions or terms, so that we could build this very complex decision boundary. For a second order set, such polynomial terms can be built like so. Now, this is only for 2 dimension, by the way. But suppose we now increase the number of features, the original features, to say 100. So instead of having just these two, now we're going to add more. And let's say we have about 100 features. So that let's just assume that we have a task of, let's say, having these samples, the being positive and the negative, in such a way that if for the positive samples, it means that that in 6 months that these housings with these features can be actually be sold, as well as those of the negative samples represents those of the housings that will not be sold. So the task here is to be able to come up with this decision boundary so that we can distinguish between those of the negative samples to the positive samples. Now, to be able to do this with an increased number of dimensions, before we only had x1 and x2, now we have 100 feature set. Then, for the second order set of such originally 100 features, it's going to be actually produce roughly about 5,000 features. The reason is because we have this order of computation, which is roughly m squared over 2 factorial, where m represents the original number of features, and the power, the square there, represents the second order set. So this means that any of the combinations, say xi and xj, can be used as those of the polynomial terms to be coinciding with each of these parameters. So once again, for 100 features, if you square, that's going to be 10,000, and you divide by 2, that's going to give you roughly about 5,000 features. So that's a lot of features. So and if you have a lot of features, that means it's going to require, once again, 5,000 parameters. As we can see that the structure of this relationship, say theta 0, theta 1, down to say theta 5,000, and then it's got the corresponding, say, x0, x1 down to x 5,000. So because they go together as with a dot product, this means that it's going to require, well, it's actually m plus 1, so actually 5,000 plus 1 number of dimensions, or the number of parameters, in order to be able to come up with a decision boundary like this. Now, 5,000 features or 5,000 polynomial terms is just a lot, so most likely it's going to introduce overfitting problem, because there are just too many parameters compared to, say, the number of samples. So to resolve this problem of overfitting, we could, for example, limit the number of features to a smaller set. So if we just include a subset out of 5,000 features to just selecting those of the quadratic terms, in other words, just square terms, that's going to just give us about 100 features. Now, the problem with that is that it's going to actually simplify the decision boundary. So only those of because these square terms are going to be surviving, what you are going to do is to have the decision boundary looking very much circular, which again is not going to be sufficient to model a sophisticated decision boundary looking like that. What if you increase the order to a third order, that is, by having a combination of x1, xi, say xj to say xk, combination of these three polynomial terms, three set of polynomial terms like this, it's going to then increase drastically the number of features because of this feature relationship operation, which again is, because we have a third order set, it's going to be m cubed divided by 3 factorial, which then would be 3 times 2. So that would be a cube of 100, or 100 to the third power, and we divide that by 6, and that's going to give us roughly about 170,000 features, which is a drastic increase in the number of features by involving a third order set for its feature. Now, why do we need a higher order set of feature? Is because we could have there could be a need of very sophisticated, very complex decision boundary that needs to be built throughout the learning process by using the gradient descent. Now, that's going to become very much problematic for even very simple computer vision problem. Suppose you have a task of detecting a car from, say, those of the non-car, pools of those of the non-car exemplars. Then what you essentially have is that you have samples of these images, where each of the image, as you can see, is huge in terms of the number of features that's going to be involved, because we're talking about now a pixel level of features, pixel level of intensity values for feature. For example, by capturing this much using a camera of, let's say, an object that's contained in this scene here, which is a car, even with a size of a very small rectangular size there that contains, say, the car's doorknob image, it's going to be read by computer a set of these, a matrix of a set of these numbers, which is converted from what the camera captures. And as you can see, because we have a grid of these numbers with each of these elements representing a specific feature, specific pixel intensity, what you're going to have is just so many numbers, a huge number of features to represent even this particular snapshot of image. So since it is an image captured by camera, the matrix as a result of conversion process from the images captured by camera into a number is going to become very, very large in dimension. As a matter of fact, with today's technology, with using even our smartphone, nowadays the number of pixels we're hearing these days is that it's going to have over 100 million number of pixels. I remember that just a few years ago that the smartphone having a camera that could actually capture images of, say, 5 million pixels for camera, that was actually supposed to be the state of the art. A few years later, which is right now, today, I'm hearing with such cameras being able to capture an images of over 1 million pixels per image. So that means that in terms of, with respect to the number of features, if you convert all these, say, two-dimensional space, the grid of the numbers into resizing it into a single column, then let's say this guy here being the very first element and the last one here being the very last one here, we're talking about, once again, over 100 million number of pixels or 100 million number of features. So that's going to become problematic for, once again, for logistic regression type of learning algorithm, because it's going to definitely introduce an overfitting problem. Now, for a typical computer vision problem, the way how we could detect, say, car from those of the non-car is by means of training with, say, a pool of those images that contains cars as objects, compared to those that of the pool of images that does not contain a car. And so we can then use both set of database, those of the cars and those of the not cars, be contained in this pool of training database to let it go through the learning algorithm. And then after the learning algorithm then converges with its hypothesis function, which is modeled by h of theta with x, where the x is the input and theta would be the those of the parameters that's represented by the learning algorithm. After the training is complete, then we can let it go through a testing by using one of those exemplars that were not part of the training set. And hopefully that if this particular image as a test set or test example contains that of the car image, should be producing the output as that of the car. Again, such a training process is not going to be trivial, as we can see and appreciate the size of the dimension that each of these images is going to actually encounter. For example, let's just go through the learning algorithm process once again. And here, what I want you to do is to recognize the location of 2 pixels in this entire, say, snapshot of an image. Let's say that of pixel 1 as well as that of the pixel 2 here. So we could have, once again, many of these exemplars and each of these examples will either contain a car or no car. So these examples are going to be injected into the learning algorithm. But here, once again, what we want to do is just looking at just two pixels, pixel 1 and pixel 2. That is pixel 1 being at this very specific location, as well as pixel 2 being at this very location. And so when we plot the locations, when we plot all of these samples with the specific pixel 1 value and pixel 2 value, where pixel 1 value is on this horizontal axis and pixel 2 value is on this vertical axis, then with the corresponding, say, pixel 1 value and pixel 2 value on this coordinate, then it's got a very specific intensity value for, once again, for pixel 1 and pixel 2. So for pixel 1 of this particular exemplar would be right here, and the intensity for pixel 2 for this, once again, sample is at right here. Then you can plot a sample of positive being located at that specific position. And similarly, if we have another car that has a very specific pixel value here for pixel 1 and another pixel value for pixel 2 right there, then we can plot that positive sample being there. And similarly, we can have, once again, other samples. Those are the samples that does not contain a car, be specifically located here for pixel 1 value being right here and pixel 2 value being here, so that location of the negative sample be here and another one being here. So we can have a number of these positive samples as well as the negative samples on that particular, let's say, plot using a one particular value of pixel location and another location of the pixel. Suppose the two locations of the pixel happens to be, say, pixel 350, which is this vertical axis, and pixel at 450 location be right here on the horizontal axis here. And then we plot those of the samples that belong to the positive, that is, those of the samples that contain the car images, and those of the negative that do not contain the car images, where, once again, each of these snapshot that contains the pixel 350, which is this vertical axis, and the 450, which is the this horizontal axis, then would actually start off with pixel 1, and then it sort of like a raster scans to the right, and then comes back here again, and so forth. And then the last one would be, say, pixel, the last pixel. And suppose, let's say that you have a 50 by 50 pixel images. So the vertical axis here is 50, and the horizontal would be 50 pixels. So together, we have 2,500 pixels, which means that the very end, very last pixel here is the pixel number 2,500. So that makes the dimension of this image, the snapshot, being 2,500. Now, this is going to be actually multiplied by 3 if, let's say, the snapshot actually contains 3 channels, RGB, the red, green, and blue. So just considering with, let's say, a grayscale, so M is 2,500, so having just a single column or a single channel. So that makes X being a dimension having 2,500. So you have 2,500 intensity, each, for example, representing the intensity for each of the specific pixel number. Now, for this type of representation, which essentially is an image of a car or a snapshot of an image, if we consider the quadratic feature, that is to have xi and xj combination for the polynomial terms, then the estimate the asymptotically, the number of the total feature size is going to be 2,500 square, and you divide that by 2, that's going to be roughly about 3 million features. So once again, even very small, very minuscule, small size of an image, just 50 by 50 snapshot, it's going to require 3 million features. Just for having, let's say, a quadratic feature terms in this, once again, parameter dotted with that of the feature. So here the column of the number of parameters is going to require 3 million parameters. So what that really means is that a simple logistic regression type of a learning algorithm will not be effective to model such a high dimensional feature for mapping, and it's going to definitely introduce overfitting problem because there are just too many parameters compared to, let's say, the number of these image snapshots or the number of samples. So that means that being able to actually build a very sophisticated and complex decision boundary for performing a very robust decision, robust and accurate decision for, let's say, classification between positive and negative in this circumstance is going to be very, very difficult. Once again, because most likely it's going to produce overfitting problem. So that's where the artificial neural net comes in, and such a model representation is going to be actually very, very helpful devising a complex decision boundary without introducing such an overfitting problem. So just to go back with the history of the artificial neural net is that, once again, the artificial neural net is an attempt to mimic like that of the human brain. This was actually was introduced back in the 50s, but widely used in the mid-80s up until early 90s. However, the popularity of using artificial neural net sort of diminished in the mid-90s. However, actually, this is because of, once again, even with the artificial neural net model, which we're going to talk about here in this lecture, it still would actually encounter overfitting problem because we have, once again, just much more dimensions required for performing computer vision type of problem. Once again, why? Because 50 by 50 type of, let's say, image might be doable for reasonable for, say, artificial neural net, but we're talking about now, once again, well, the 50 by 50 is roughly 2,500 number of features, but we're talking about 100 million, right? 100 million features this is for each snapshot. So it's going to actually encounter, once again, the overfitting problem as is, because of the lack of two things. The lack of this is because of, number one, because the lack of computational power. Back then, we didn't have what for example, what we enjoy today, like GPU type of processors that would actually accelerate images for performing processing. And then there's a lack of database, or simply called the DB, that would have the labels associated with each of these snapshots. Because once again, in order to accommodate a very large dimensional feature size, we need a lot of these samples, right? Which is what we saw when we talked about the overfitting versus the generalization problem in the past. However, because these two problems were solved these days, we now are enjoying a big resurgence of the artificial neural net. And that's been sort of like the state of art technique for many of the applications under the name of deep learning model, which is essentially the artificial neural net model with much more sophisticated by building many more layers on top of it. So let's now describe about artificial neural net model and the way how, and as I said before, how this artificial neural net model mimics like that of the human brain. And the emphasis here is that that we think that there is one learning algorithm, which is actually a hypothesis by neuroscientists because they have done a couple of experiments to show that any specific, let's say, locations in the brain performing, let's say, a specific perception or learning. Let's say, for example, like that of the auditory cortex. So there are a number of cortices, which are the brain tissues in the brain, and it can be like that of the human brain or any animal brain and so forth. That there are specific locations in the brain which is dedicated to do a specific sensory operation. For example, the auditory cortex in human brain is is dedicated to perform, say, perception on hearing, and another cortex called visual cortex in human brain. What it does is that this cortex in the brain tissue, a specific location in the brain, is dedicated to perform, say, visual scene understanding, and it is directly wired to that of the eyes. And similarly, there is also a somatosensory cortex in the brain, which is dedicated to perform, let's say, touching type of sensing. Now, what the neuroscientists did successfully in the past, using the experiment by using, say, not human brain but animal brain, is to show that by disconnecting, by cutting off the wiring between, say, the ear to that of the auditory cortex, and then wire the eyes directly to that of the auditory cortex, then this particular the brain tissue, which is the auditory cortex, learns to be able to see. In other words, that with this directly wiring of the eyes to that of the auditory cortex, now this particular brain tissue can see and perform scene understanding. And similarly, if we do the same, once again using the somatosensory cortex, disconnect the sensory or wiring between the touching mechanism to that of the somatosensory cortex, and then wire directly of, once again, the eyes to that of the somatosensory cortex, then this cortex now, once again, begins to see as if this somatosensory cortex is like that of the visual cortex. So essentially what this experiment does is to show that there's only one learning algorithm that can be trained to do any of the specific tasks. It's just that we have different, brain tissues performing different perception, specific, say, perception, because they are just wired that way. However, if we rewire, once again, like that of the, say, wiring mechanisms from that of the eyes toward directly to that of the auditory cortex, we can train any of these brain tissues to perform any task that we want, rather than needing to have for example, three separate learning models, three being, let's say, the visual, the auditory, and the somatosensory cortex. So this means that, if we have, like, say, about 1,000 different tasks, you don't really need to have a different set of brain tissue to perform all different tasks. Rather, what you really need is just a single one learning algorithm that can be trained to do any of the specific tasks that you train it with. Let's look at another example of such a brain case that is using just considering that any of the brain tissue can be learned to do a specific function. For example, here, um, what this picture is trying to show is that the tongue, your brain can be learned to use your tongue to be able to see. For example, you have a camera that's mounted on your head, and then the output of this camera is connected directly to this, let's say, wiring mechanism, where the wiring mechanism actually has these pixel elements, and depending on what is actually being shown or being captured by the camera, it's going to either activate or stimulate a specific pixel location. For example, if it sees some dark elements or dark say components within the scene, within the say the field of view, then it's going to, let's say, activate a specific pixel value here. Or if it sees something very bright, then it's going to also, let's say, activate or stimulate a specific location of this, let's say, um, uh, the stimulating, let's say, wire that's actually attached to your tongue. So this means that you could actually train your brain to see through your tongue. And similarly, you could actually have the brain learn, your brain being, for this person being obviously a blind, can learn to see by hearing or by using your once again auditory cortex. Now, you can have this echolocation type of, let's say, behavior for this particular person, for example. That is, this obviously this person is blind and cannot see. However, by generating a sound by using, say, his finger snapping or clicking his, let's say, a tongue, he can actually produce certain sound where his auditory cortex, through his ears, can actually see how the sound becomes reflected and bounced off of these obstacles that's in front of. In other words, this person can actually navigate through these obstacles by constantly creating these finger snapping sounds, and he can hear the direction of the echoes so that he can navigate through, which essentially is that he could actually see things by using his um, auditory cortex. And similarly, the same, let's say, person who is blind can have this haptic belt, let's say, mounted on his waist, and let's say with all these sensors is actually a buzzer around the belt, which can actually be activated be, uh, because it's got this magnetic compass, so that any specific location, let's say this one here, can actually tell the direction of the north. And once the direction of the north is detected, then simultaneously the buzzer will make a certain sound, or it could actually make certain vibration and so forth, so that the person who's wearing this haptic belt could actually feel and has then the sense of direction. And once again, you could actually add the visibility with having another, say, a third eye implanted, like the way how this frog has a third eye, and hopefully having a third eye would actually increase the ability to see much, much better. So all of these pictures are showing different type of mechanisms or experiments that the brain can be actually learned to do, other things than what it was previously learned to do. For example, once again here, the brain is learning to see by means of sensation through the tongue. And here, the brain is learning to see by means of hearing. And here, the brain is learning the navigation or being seen or having this sense of direction by means of using this magnetic compass that's wearing around his waist. Okay, so that's what we're going to be doing is that we're going to essentially consider having a one learning model that represents the brain, and that learning model can be started with a neuron mechanism in the brain. So here's a slide that shows how the neuron is structured physically. So neuron, for example, a single neuron has a nucleus, which is essentially at the center of the neuron, which, by the way, performs a couple of nonlinear functions there. And then as a result of stimulations or excitations coming from the dendrite as the input, it produces its activated, say, value at the output by means of the axon. So a typical neuron will have the connecting mechanism that sort of like wires from the output to the input side by means of the dendrite. So that would be considered as the input wire. And then once again, as the signal that comes in through the dendrite will actually activate this neuron and then produces certain output. And the output then is going to go out to its neighboring neuron by means of the axon, and axon is then considered as the output wire. Now we have roughly around 86 on the average billion number of neurons in a human brain. So just to, as a rounding number, we can just say that it's about 100 billion. So let's just consider that we have about 100 billion neurons, which is 10 to the 11th power for each of the human brain. And each neuron has connections to its neighboring neurons to about 10,000 neighboring neurons. So this means that we have a total of 10 to the 15th number of connecting synapses in human brain. Now 10 to the 15 is like 1,000 trillion. So this means that between a neuron to another neuron, you have this connecting wire, and this connecting wire is also called synapses. And how many synapses do we have for each of the human brain? Roughly about 1,000 trillion, or 10 to the 15 number of connecting wires. So this is where the synapse is going to be considered as the way how it's going to perform in terms of the parameters, as the way, if you can visualize yourself comparing it to the logistic regression formulation. So each of the synapse is, for example, a specific parameter, a value, or a weight value. Now, so that we could actually represent the entire neuron in the brain into a computational model. So let's just say that once again, you have a neuron here with the nucleus. So here inside of this neuron, you have essentially two major functions. One is to perform an aggregation, and second is to perform a nonlinear mapping. Now, what's actually coming into this neuron would be these feature values that are performing certain excitation, and then each of these feature will be aggregated by means of these connecting wires. And these connecting wires has certain weight value. So these weight values will be denoted by theta sub ij. So the theta sub ij would be the parameter or the weight on the link or the connections from unit j to say unit I. So if you consider this as the unit j, which is the source, and then I, which is, let's say, the destination. So this means that you have a weight of theta sub ij, meaning that you have a weight between, say, jth element or unit to that of the ith unit. And of course, you have, many number of these features, not just one. So we could have, for example, theta 1, theta 2, down to theta, say m, number of say feature dimension. So each of the sample as it goes in could consist of say m dimensional feature. And once again, each of these feature would be then aggregated to along with by performing a dot product between once again the parameter. So this aggregation is denoted by net sub I, where the net sub I is essentially a weighted sum of the features, where that weighting is done by the parameter value theta sub ij. So once again, it does perform aggregation or performing a weighted sum of the input features by having these input features multiplied by each of these parameters. And the second function of this neuron is to perform a nonlinear mapping. And a typical nonlinear mapping is, if you can recall the logistic regression formulation, that this nonlinear mapping is done using a sigmoidal function. And this nonlinear mapping then goes into it's going to go to other neurons connected by means of this output wire. So the output as a result of performing this nonlinear mapping is the value of the output denoted by a sub, let's say a sub I. And then you have this nonlinear mapping, which is also called activation function. So this is the modeling of a neuron in terms of its computational, let's say, behavior or computational model. Okay, so with all that, let's talk about the structure of the artificial neural net. Not just having one particular, say, neuron, but let's say that what is the simplest form of artificial neural net? It's called perceptron. And what this perceptron does in terms of structure is exactly this. That is, that it's got once again a feature that goes into as an input. Then it's got these connecting wires, where the connecting wires would be represented by its corresponding say parameter. Say for example this one here theta 1, the next one is theta 2, and the third one would be theta say 3, where because it is all connected to say ith neuron, we then give say I here as index. So this would be theta sub I1, and this one here would be theta sub I2, and then this connecting wire would be given as theta sub I, say, 3. Okay, so this is the perceptron with just having the input layer and one hidden layer, or with a one single neuron, where this single neuron, once again, as I said before, performs two different tasks. One is the aggregation of the input by means of having a, say, weighted sum of the input, where the weight is done by the connecting wires parameter value, theta sub ij, which is multiplied by each of these input feature. So the net I is that computation. It's the computation of the weighted, say, input feature. And the second task is to perform, once again, this nonlinear mapping, where a typical nonlinear mapping is by using a sigmoid or logistic activation function. So this is the perceptron, the simplest possible artificial neural net model. And we just showed that the typical activation function, it would be that of the sigmoid function, which I'm sure that you've seen it so many times now, because the same sigmoidal function was used in the logistic regression learning model as well. There are like other activation functions as well. For example, this would be the step function, where for step function essentially says is that if the net value is greater than equal to, say, t, which is a threshold, then it's going to be +1. Otherwise, it's going to be 0. And for the sign function, activation function would be that if the net value is greater than 0, greater than equal to 0, then it's going to be positive, +1. Otherwise, it's going to be -1. So this one here is bipolar, +1 and -1. This one is unipolar. This one here is also unipolar. You could also have a hyperbolic tangent of, say, net, where the hyperbolic tangent is essentially looking similar to the sigmoid function, but it's actually bipolar. It's a big say, S shape, and the highest point of this big S shape is +1, and the lowest point would be the -1, as opposed to, say, 0 to 1 here for the sigmoid function. And the hyperbolic tangent is going to be actually useful in the training algorithm using artificial neural net, perhaps more so than that of the sigmoidal function, which we're going to show that later in the latter part of the lecture. So, by the way, the hyperbolic tangent, the representation of it is similar to the sigmoidal function. It's actually 1 over 1 plus e to the -2 net, and then it is subtracted by 1. So this is that function for the hyperbolic tangent, whereas for sigmoid function would be just 1 over 1 plus e to the minus net sub I. Okay, so what? Well, actually, the beauty of artificial neural net is that you can actually build more layers. Here, for example, let's just say that we increase the number of layers from that of the perceptron with just having a one single output with a neuron, whereas the input side was just those of the input layer. Here we have a 3-layer model for artificial neural net with, let's say, the first layer is the input layer, as before, like that of the perceptron. And then layer 2 in this architecture is considered as hidden layer because the third layer, layer 3, would be considered as the output layer. So if you can see that what is accessible from outside or what is being visual from outside would be just the input layer as well as the output layer, then the hidden layer is actually not visible. So that's why we can say that layer 2 is hidden layer because it is in between, it's sandwiched between the input layer as well as that of the output layer. And another thing that should be also considered would be these bias units. For example, x sub 0 and a sub 0 would be considered as the bias units. So typically the bias units would be given with a value of 1. And what is then going to be important would be the specific weight value, which is the weight or the parameter that's in between connecting, say, x0 to that of the hidden layer neuron there. Now, I just made the notation for, say, the number of layer. Let's say being a layer 2, I am using the superscript to represent the layer number. For example, this one here, being layer 3, I'm using, say, A3 here, superscript, to represent the layer number, and then using the subscript to represent the unit of the hidden layer. So for layer 2 of the hidden layer of the first unit of this let's say layer 2 hidden layer would be denoted by a sub 1 with a superscript 2. So this represents that it's the neuron at layer 2, which is the first unit of the neuron, say, pool within, say, layer 2. And as you can see, all of these features, as well as the neurons, are all fully connected. As you can see, so each of these connecting wires are made completely between, let's say, layer 1 to that of the layer 2 and so forth. And so this is how the architecture is going to be denoted in terms of, for example, how we can identify in the notations. Okay, so furthermore, let's look at the computation of how things are happening at each of the layer. Once again, I am going to be using a sub I with, let's say, j being at the superscript there, is to denote the activation of unit I in layer j. So this one here is the layer number, and this one here would be the unit number. And similarly, you would have the matrix of the weights controlling function mapping from, say, layer j to that of the layer j plus 1. So this one here represents those of the matrix that represents the weights, say, from layer j to that of the layer j plus 1. So for example, if you have theta that's representing right here, let me just say that because it's now a matrix, I'm going to be using a Greek letter that which is represents, which typically shows that it's an uppercase Greek letter, theta. So I'm going to be using this to denote that it's a matrix. And once again, if the superscript represents the matrix, the weights controlling from that of the layer j to layer j plus 1. So this means that if we have a matrix that is represented here, this means that it's going to be equal to theta of, let's say, of 1. So, for example, let's say that this neuron here, so that's the neuron, because we're looking at, say, the second layer, which is right here, and this with the very first activation. of that neuron. So that activation is mapped by this nonlinear function g, and inside of this bracket is the, once again, the net. Remember the aggregation by means of net function. So net, let's say in this case, would be equal to net I is the aggregation of all the theta, all of the parameters. Let's say 1 to say j, which is multiplied by x of say j. So this means that we have roughly, this is going to be equal to essentially this. So here, in this case, by the way, this one would be a vector, because what you have here is just a linear sum. So this means that for this particular neuron, every connecting wires would be represented by these parameters, a vector. And then you have the input feature represented by x of j. So this is essentially performing, once again, theta, say, let's say theta dotted with that of the x vector, where the theta vector that you have there is the one that essentially it ends up going toward, say, first unit of the neuron. So I'm going to actually put 1 there to denote that it's the it would be all of those all of these weights that goes to, say, unit 1. So I should also in place that this is at say layer 1. And similarly for the second neuron, we do the same. And here we have the weighted sum of all those connecting, say, wires, this one, and then this one here, from these features, as including that of the bias value there. So we have that. And the third one, for example, this one here, once again, inside of the bracket would be the weighted sum of all these features, with each of these weights would be represented by those connecting wires from each of these features. Okay, so then let's move to, say, this is so layer say 2. This one here would be layer 3. So then the third one here, this neuron here, would be represented by 3, as the superscript represents 3 as being located at layer 3. And because we only have 1 unit, I'm going to still use say subscript 1 to represent this as the neuron. So that neuron, once again, what it does is that it performs this nonlinear mapping using, let's say, sigma order function. And inside of this bracket here, or parenthesis, would be the linear sum of all these as the feature multiplied by these weights, which is represented by here. Now, if the network has S of j units in layer j and S sub j plus 1 units in layer, say, j plus 1, then this theta sub j, let's say either this or this, because you only have 2 set of matrix, will be of dimension of S sub j plus 1 to that of Sj plus 1. So this 1 here comes in because of the bias. For example, once again, for the case of, let's say here, you have this theta matrix So the theta matrix would be that of, say, 1. It's going to then contain, as we saw, it's going to be having, say, dimension of 3 by 4, because you have 3 that's leading to these 3 neurons, and 4 because it starts off with 3 features as well as 1 more for the bias. Okay, so it's going to be 3 by 4. In other words, as you can see, we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, where each, let's say the third one here, let's say the second one here would be this, right? Would be theta, so theta of, say, 1, 1, 1 times, say, x1, okay? So this would be having a matrix with, by seeing what is in front of, which is right here, the toward the destination, as well as where it came from. And where it came from should also have this bias unit there added as well. Okay, so we're sort of like looking into an artificial neural net model, a typical artificial neural net model, and we're trying to show the computational side of the artificial neural net. And to be able to perform the computation, we actually have to appreciate the notation of how each of these elements are being represented. Once again, we have a 3-layer model. So layer 1, layer 2, and layer 3 here, where each of these layers would be modeled or represented by the superscript. So in this case, which we just talked about, right? The third one here, which would be this. So the neuron at the third layer would be represented by this nonlinear activation function. Now, we could also talk about a little bit more details of how the values are essentially computed at each of the layers. For instance, Z, remember Z would be the same as the net, or the aggregated sum of the weighted input features. So this is same as net. So net of, say, well, not a unit, but net at, say, layer 2. Okay, so net at layer 2 means that at the input, at the destination of these connecting wires, you essentially have this type of computation, which is the dot product between the input to that of the connecting, say, matrix of these weights. So this is what the weighted, the linear is an aggregation of the weighted input features, and then we have the output here, the neuron at, say, layer 2, which would be essentially a nonlinear mapping of these 3 specific, say, net values, or that would be Z1, Z2, and Z3. And at that point, what you do is that you add a bias there, along with other, say, neuron outputs. So that's going to then produce say, Z3, which would be the net values or the weighted sum of these new features, which is computed in terms of the neuron outputs, A's. So Z, so the Z with a 3 superscript would represent the dot product between the A matrix right here, theta being the parameter matrix, which is dotted with the of these inputs, where once again the input then would consist not only these three elements, but also adding this bias there as well. Meaning that once again, A is going to be actually, let's say A0, say 2, A1 of 2, A2 of say 2, A3 of 2. So you have 1, 2, 3, 4 elements to represent that of say A vector. Previously, the A vector seems to have here, as you can see, just those of the three elements, but now with a new A with a superscript 2 should contain 4 elements, and so as a result being that this 4 element vector of A is dotted with the 1, 2, 3, 4 element say matrix, and so this is, which is actually, as you can see, it's just a vector. So that would be the result for Z3, which is actually a dot product between these 4 elements of A to that of the 4 elements of these weight vector. And so that's going to be used to compute the output at this neuron at layer 3. So this is the right process for computing this activation, this nonlinear mapping of Z superscript 3. So that's going to be the prediction like that of the output. So if you can consider by emplacing a box here, this would be the input side of the box, and this would be the output of the box, where the whole thing is considered as the INN model. So you have the input that's connected from outside, and then the output then should be the value for the prediction, which then can be used to, that goes into another set of the neurons, or just being worked as our prediction for the artificial neural net model. Okay, so I sort of like alluded to that idea. So why are we adding more layers? So adding layers essentially is,